Yeah, sunny morning, hot morning, and an extra good morning. Why this happens to be an extra good morning? A couple of days back I have mentioned that slowly we are keep listening to good news regarding all those relaxations of lockdown time and also some decisions from the government. So in such case, yes, extra good morning. Dates for our CET has been announced. 30th of July, 31st of July. One more time, a long time for again preparation, revision and whatnot. You can have your second revision, third revision, fourth revision as well. And I wish those of my Vijayarthi hunger about this exam and result will make the best use of again 2 months. Because 2 months happens to be double-edged sword. For most of the students, it will be a kind of discomfort because maintaining stamina for further 2 more months is very difficult thing. So those students with right stamina, I wish they do that 1 hour extra work in the day, that extra hour, the walk of extra mile, making you that extra during your examinations and more important towards result day. They have definitely that extra edge. So I wish this is a really extra good morning for all of us. Now coming to our session. Our discussion of AC currents. Last class we have seen how to discuss an AC circuit. And today the most important case of LCR series circuit. First let us discuss all the parameters and other specialties of this one. Now here we can find a resistor, capacitor and inductor to an AC source E0 sin omega t. One more time, not always sine, it can be either sine function or cos function. Now first let us write the 4 important terms. The one is the reactance in the circuit X is equal to, earlier discussion we have told, since both L and C are present here, both L and C are present here, it is the case of both XL and XC, and the effective is, yes, XC difference XL, higher value minus lower value. So this is what is 1 upon omega C minus omega L, omega, yes, the frequency of this given source. See, I am listing out these parameters, and in our examples it is a straightforward substitution. Look at the data, what is that is required. The first one, reactance, and therefore now comes the impedance. Hope you remember those 6 or 7 that we have listed in the last class. Z, the impedance is under root R square plus, yes, X square, that is 1 by omega C minus omega L. This one squared, right? The impedance. And since we know X value, now we can also write for the phase difference. Phi is equal to tan inverse XC, that is, I will give a substitution as well, 1 upon omega C difference omega here. See, one more time telling you, this is the difference that I am taking here, higher value minus lower value. It is negative, or the what is that difference that we are taken. It can be XL minus XC or XC minus XL. So this is 1 upon omega C difference omega L by R, because this is our definition. Remember, tan phi is equal to X by R, definition of phase difference. Now, after that, of course, you can also calculate the power factor cos phi as, you remember, cos phi is R by Z. R is the resistance in the network, and of course, you have calculated like that. Now, these are straightforward questions in your data. Now, coming to the other significant points regarding LCR circuit. Remember, this LCR circuit is what is called as a tuning circuit, and why we use all these LCR circuits and all is, last class also we have told in the case of electromagnetic induction, LC oscillations, what is called as an oscillator, to produce required AC signals of required frequencies. So now cos phi is equal to R by Z. Now let us come to the significant point. That is what is here in this case. Now three cases will arise. What is that? Case 1, as I have shown, if XC greater than XL, inductive reactance lesser, capacitive reactance is more. And according to our earlier discussions, we know that both are of opposite nature. They are opposite phase when we are writing as a phasor. Therefore, what is this XC? XC greater than XL means voltage lags current by phi, and that phi, of course, we have given this expression. Now what will be the case 2? Case 2, XC less than XL, that is XL, inductive reactance greater than capacitive reactance. One more case. So in this case, it will be other way around, that is voltage leads current by phi. I told you when it is the question of phase difference, be careful about leading or lagging. Now I am taking the case of voltage, and with respect to current I am writing. Therefore it was here voltage lagging or else current leading. Here I said voltage leading, current lagging. Now the most important case of our discussion would be XL equal to XC. And that is why whenever any example on LCR series circuit, soon you find the data in the question, you have to verify the values of XL, that is omega times L 2 pi FL, and XC values 1 by omega C. 99% of the examples will find that XL is equal to XC. If it is not the case, then this concept of phi will arise, and which is leading, which is lagging, that will be the case. Now since we have taken this special case XL is equal to XC, all these equations now we will find a change, or we get special cases. What is that? XL is equal to XC, net in reactance is 0. You just follow now 3 or 4 lines that we are writing, which are all substitution in this one, not a case of memory. Net reactance is 0, therefore Z is equal to. Now here we have shown XL difference XC, we have shown here, if this value becomes 0, then you will find that Z is equal to, Z minimum is equal to R. Z is equal to Z minimum is equal to R. And therefore now substitution of this case in the phase will also give you that phi is equal to 0 degrees, which means that voltage in phase with current or vice versa, in phase with the current, in phase with current. Now how to understand these things in the figure? Supposing in the same figure we are now showing voltmeters. Supposing here I have fitted 3 voltmeters. One voltmeter across resistor, the other one across capacitor, and of course the third one. Now, supposing I call this as VR, VC and VL. Earlier we have mentioned only about these X values, reactance for inductor and reactance for capacitor. Now, when we are writing the other cases, see here, what is VR? If I is the instantaneous current in the circuit, VR is equal to IR. Our result from current electricity. And now what is V across C? V across C is equal to XC times I times XC, and hence you can also write VL, the voltage across inductor is current times XL. Current times XL. So individually asked to calculate the voltages or the voltmeter readings. So these are the values that we get. Now in this case, the case XC greater than XL. Now here, earlier we said voltage lags current by phi value. Of course, not taking the case of XL is equal to XC. Now, in general case, we are taking such that we can add one more statement here. XC greater than XL. Here, what you find is that VC greater than VL. Similarly, if XC less than XL, what we find is VC less than VL. Now here we said XL is equal to XC. Voltage in phase with current is one result, of course. The other result is also important. What is that? V across C is equal to V across L. V across C is equal to V across L is the case. Now, one more time. Now we have taken VR, VC and VL, the three voltages. Last class we have told why we use the concept of phasors in AC. Though currents and voltages we are dealing with, and both, they are being scalars. Why the concept of phasor? Because AC voltages, AC currents, and for that matter reactance also, they follow the laws of vector addition, and that is why we have taken them as phasors, which are taken as rotating vectors. Therefore, now what is the relation between these three voltages is another very important topic. It can be a very, very tough question as well. You see, now here three voltages are there. This is the applied voltage. Therefore, now we relate them as E is equal to under root VR square plus VC difference VL whole square. So this is one important result for LCR circuit. Remember, in our discussion about 5 to 10 minutes, many things it will appear as tidbits, but all of them is not a memory. As I have told you in our last discussion that for any AC circuit, 7 parameters are required, in which 3 are the first resistance, reactance and impedance. After that, the phase difference or the power factors we can easily write it for. Now when it comes to the question of LCR, the discussion is a bit further, taking the values of XL and XC. And that is why any LCR circuit example, when data is given in terms of numbers, capacity, capacitor values, inductor values, you check for XL and XC. And as I have told you, 99% will be given the case of XL is equal to XC. Otherwise, all these things are now possible. E is equal to under root VR square. You see what you this observe? This you observe it as R equal to of P square plus Q square, the 2PQ cos theta term becoming 0 like that. So E is equal to VR. Therefore, now if I have to show you this LCR circuit is a phasor, for the analysis, if I take it as a phasor, if I take this as a phasor, a beautiful and intelligent aspect. Now we know that what is the concept of XL, current, lagging voltage, and for due to XC, voltage, lagging, current. Therefore, here if I show a general case, what is that? If this is what is VR bar, this is the voltage phasor across resistor, then we know the property of that back EMF nature of inductor, current, lagging voltage. Therefore, this it will be like VL, the voltage phasor for inductor, and this will be exactly anti-parallel other phasor VC bar. Now here in this depiction, what you observe is that this angle is right angle and this one is also right angle. These phasors are anti-parallel. One more point is that you will see I have taken the magnitude wise. This is of more length and this is of lesser length, which means that in my representation, this voltage across capacitor, instantaneous values we are writing, this voltage across capacitor is greater than voltage across inductor. So these lengths are also very, very important. Therefore now for this, if you extend this phasor, what is that you get? This phasor is of course this is VR bar, and since this is higher value and anti-parallel nature, this is what is this VC bar minus VL. Now these two are at right angles and therefore this result will come. So this is how we do the things. The relation between different voltages is a very popular example, right? All these voltages, and even in terms of phasor also. And as I have told you, any phasor representation is not a unique representation. Supposing if VR bar is shown in this quadrant, so for that you may be asked to write the other phasors of VL bar, VC bar and so on. So about phasor we have told, and one more time I repeat that. In the anti-clockwise direction starting from positive x direction, the phasor that appear will be in leading phase, whereas in the clockwise direction, if we count, the phasors that appear will be lagging in phase. This we have stated already in this one. Now, one more time, let us come to that discussion where we have left. See, voltage in phase with current is one important thing, and another one is VC is equal to VL. VC is equal to VL such that VC minus VL is equal to 0, or VC plus VL is equal to 0 is one important thing. Why? Because of the opposite nature. Here you will find VC minus VL. This is not algebraic addition that you are getting, it is after phasor you are getting. Therefore, equal means here V across R is equal to E. VC is equal to VL, one result, and V across R is equal to E. All these things can be asked in terms of voltmeter readings. Suppose here, I show you one example. Suppose he says this is 250 volts, 100 hertz. Such a source I have been using. Now here, the numbers are now given. Suppose I said this number is 120 volts. This number is, suppose 160 volts. 160 volts. No, I will write this as 120 volts, and this is 160 volts reading. Now what will be the value across this voltmeter, across this resistor is a question. Now for such question, this is what is the answer you will get. So this E is equal to, so this is how you will substitute the values and relate all different voltages. See, voltmeter. 3 voltmeters have shown, and each of them across one of them. See, V across R, 1 voltmeter, V across C, 1 voltmeter, V across L, different voltmeter. Supposing in the same example, I show a voltmeter like this. Suppose this is what is V1 and this is what is V2. This is V1 and this is V2. Here the answer is, suppose 250 volts. Because for our NEET and CET examinations, very similar examinations, if you are good at concept, you got the answer. Suppose if this is what is 250 volts, what is the reading of V2? If we use this value, remember, already E is equal to VR, that has become 250, all appearing across R. So VR is equal to E, definitely it demands that this VC difference VL is 0. Now look at this V2. V2 is not across C exclusively, or it is not across L exclusively. It is L and C. For that series we are taking this voltmeter reading. In such case, looking to the numbers and understanding and linking with our concept. So this is already 250. This is E is equal to VR. Therefore this term should be 0. Like that. So different voltmeters asking for voltmeter readings, or voltmeter readings are given, asking to calculate the values of L or C. Whole lot of changes can be made and we can create good number of questions, which of course we'll do in the latter stage. Now, VC is equal to VL for this reason. Z is equal to minimum, VR is equal to E. All such conditions, what is we call as resonance. Now we say this is the condition for resonance. Resonance is such a phenomena in the nature wherever we have the case of receiver and transmitter. Remember concept of resonance. Where does it arise? In all those cases where we come across receiver and transmitter and receiver and transmitter. Receiver will gain the maximum power from the transmitter. That condition is what is referred as resonance. Ultimately, what is the consequence of resonance? Maximum efficient transfer of energy from transmitter to receiver should happen. As I have told you, all these LCR circuits are tuning circuits, and that is why that resonance condition is important. So now in the resonance condition, now let us write XL is equal to XC. XL is equal to XC. Therefore, omega naught L is equal to 1 by omega naught C. Why we are specifically writing omega naught? Why not omega? We'll have a discussion for that, you will understand. Because as omega value changes, omega L and 1 by omega C values changes such that for one particular value of definite value of omega naught for a given pair of L and C. Now here L and C is a given pair. For that given pair, for a particular value of omega of that source that we have applied in the circuit, this is possible, that is XL is equal to XC, and therefore this omega naught is 1 upon root LC. 1 upon root LC, otherwise F is 1 upon 2 pi root LC. And this is what is resonant frequency. Again, RHS, LHS, understanding the relations, factors affecting the frequencies and all. So now this frequency independent of R value you can see here. So in the given LCR circuit, resonant frequency, I will write it as F naught. This F naught depending on L value and C value, both inverse with square root you will find. So these are what are the examples. To given example data you will find the changes in the value of L, or the changes in the value of C, the changes in the value of F. 3 terms are there. Any 2 terms changes, asking for the third one. Of course, including with the percentage changes. These are the examples that you will find this from this. And also you will find, supposing if I am drawing a graph, which graph I am writing, supposing he says, which of the following graphs best represents the variation of resonant frequency with the value of L in a circuit. Supposing L value is changed in a circuit and corresponding changes, what all happens with respect to resonant frequency. Now what is the relation you find? For any graph, the shape of the graph depends upon the relation that you find between the 2 parameters. Here what is the relation that you got? Frequency F proportional to L rise minus half. And any such example y proportional to x power n, in general I am telling you, n can be positive or negative. In the given example, we got it as some negative index. Y proportional to x power n, we will write it as a curve with the variable slope. That is, it's a non-linear curve that we will get. Remember, y proportional to x power n, yes, it is always non-linear, 1 point. Second point is, supposing non-linear, second point is if the index is positive, the slope is positive, and the index is negative, slope is negative. So it is non-linear curve. Now how to see whether it is a curve with positive slope or negative slope? Yes, again by the nature of the index, n value positive slope, n value negative slope. And one more important point to be remembered is that this value, apart from being positive and negative, we will also take one more thing. If suppose n is less than 1 and n is greater than 1, n is greater than 1, n is less than 1, then what happens to such case? So all these things are very important. Already we have discussed all these things in our classroom. In this session, I don't find time for that. Therefore, if any of the students want any clarification on that, yes, you have my contact. You can find my contact in the YouTube link as well. And I hope you will clarify that through personal interaction. So this is how we will look at any of the equation. You have a result, LHS or HS, what kind of relation, what type of graphical analysis, etc. Now, after finding this, the most important point that we are now going to write. See, in the concept of resonance of LCR series circuit, the frequency term, the parameters, finding the relation between them is a very important concept for exams. After that, let us discuss one more important topic for our resonance concept. See, in the resonance, net reactance is 0 and hence the impedance is minimum, and that minimum value is what is capital R. Of course, along with, we have mentioned one more result, remember, VL and VC, the values are equal, and because of the reactance nature, they will be in opposite phase. VL bar, the phasor of voltage across inductor and voltage phasor across capacitor, magnitudes equal, but they are anti-parallel phasors, and therefore voltage across R is equal to applied voltage. So this was our discussion. Now right, you see this I0 value, we write it as E0 by Z, E0 by Z. I0 value is E0 by Z. When Z becomes Z minimum in the case of resonance. When Z becomes Z minimum, this I0 becomes I0 maximum. Generally, when we write it for a current signal or voltage signal, of course, the instantaneous current keeps on changing. You leave that aside. Now we are talking particular value, that peak value I0 itself is a variable. I0 becomes I0 maximum and it is E0 by Z minimum is R. Therefore, this I0 maximum now depends on capital R, and you will find this as an inverse relation. So with the value, with the change, with any of the changes in R, we have to estimate the changes that happen with the I0 maximum also. Now, to understand this thing, we have plotted a graph with the omega, the frequency of applied source, versus the I0, which is given by E0 by Z actually, E0 by Z. This value taken on y-axis. So now we find that because both XL and XC values, they depend upon omega. Initially, when omega is very small, we know that XL value is omega L and XC value is 1 by omega C. Therefore, initially when omega is small, XC will be greater than XL. Later, as omega increases, what happens? XC values gradually decrease and XL values gradually increase. Right? Look at those omega L value and 1 by omega C value. So initially, when omega is lesser, I will cut this into two equal halves because it's a smooth curve, smooth symmetric curve that we get. Smooth symmetric curve, and this is what is referring to our I0 maximum. This is what is I0 maximum, E0 by R. The value depending upon, of course, R. Now, before this particular frequency or beyond this particular frequency is an important discussion. Supposing now this is what is I0 maximum, the condition for resonance, and therefore this frequency refers to omega naught, the resonant frequency. Therefore now omega less than omega naught, what will be the case? Omega less than omega naught, here what we find is XC greater than XL, such that VC greater than VL. VC greater than VL case arises. Whereas in the other case, omega greater than omega naught, if we take the other way, then we find that XL greater than XC VL greater than VC cases will arise. Instead of giving numerical values, supposing if it is in terms of graph, and ask what will be the case supposing this is at some frequency omega 1, other frequency at omega 2. So the concept is all about, I have told you in the very beginning, to know about the relation between omega XL and XC, depending on the value of L and C, which is more, whether they are equal or unequal, which is higher value. That is the key for all these solutions, remember. And now the common sense says that exactly at omega is equal to omega naught, XL is equal to XC. Before and beyond exactly at omega naught, it is the case of resonance. XL is equal to XC, VL is equal to negative of VC if we are writing its magnitude to show the anti-Phasor nature of the phasors, like that. And now, as we have mentioned, see, this value of I naught maximum depends upon R. Supposing if this is for some resistor R1 and I decrease the value of R, naturally this value will increase. Therefore, what we find is, yes, this is for another resistance. Please make it sure it's a symmetrical. If this is for resistor R1 and this is for R2, then it is R2 less than R1. R2 less than R1. So higher, the peak will gradually increase, and then you can be asked to compare the resistors, and equality, inequality between those resistors is also an important question. Now, in this example, one more important concept is, see, smooth symmetric curve, smooth symmetric curve, smooth symmetric curve, and this value is what is earlier taken to be resonant frequency omega naught, where this is I naught maximum, and we told at resonance it is the maximum efficient transfer of energy from transmitter to receiver. Hence power in the circuit is maximum. When power in the circuit is maximum, now I am taking two more frequencies where power becoming maximum, that is I naught also, I naught maximum becoming maximum. Now I am taking the case of, here I am taking this one, which is I naught maximum by root 2. So what is your take from this? When current becomes 1 by root 2 times, power P proportional to I square. Current becoming 1 by root 2 times, power becomes 1 by 2 times. So this current now refers to half power frequencies. Which power? Half of the maximum power. This I naught refers to, the I naught maximum value refers to the maximum power, that is the case of resonance. Now supposing I am considering few more frequencies apart from resonant frequency. Which are those frequencies? Now I am taking this value, if it is in terms of current, as you can see 1 by root 2 times, and if it is in terms of power, it is what is P maximum by 2. Now supposing if I cut this graph for the at I naught maximum by root 2, what we find is that it cuts the graph at 2 points which are symmetric about this omega naught. Now I am writing these frequencies as omega 1 and omega 2. So what are the specialities of omega 1 and omega 2? Right. At omega 1 less than omega naught I have taken, and naturally at this point XC greater than XL. Such discussion you please try to add into that. Omega 1 less than omega naught. What is happening? I naught value is I naught maximum by root 2, and hence power P is equal to P maximum by 2. Similarly, omega 2 greater than omega naught also the same situation arises. Hence, these omega 1 and omega 2, they are called as half power frequencies. Now let us take up that. So this omega 1 and omega 2, they are called, yes, half power frequencies. Terminology is very important. We will now find some results as well, expressions as well, to calculate those numbers. Omega 1 and omega 2. Of course, first we begin with, we know that what is that omega naught is equal to 1 upon root LC. 1 upon root LC. Now, this omega naught minus omega 1 is equal to omega 2 minus omega naught is one important case. Because we have told both omega 1 and omega 2 are symmetric about this omega naught. Therefore, omega naught minus omega 1 symmetry equation we get, and therefore now this beta is equal to 2 times of omega naught minus omega 1, or else 2 times of omega 2 minus omega naught is what is called as bandwidth. Bandwidth definition. Bandwidth definition. What is bandwidth? The difference of half power frequencies. Bandwidth is nothing but omega 2 minus omega 1. Supposing if I take this as delta omega, this is also delta omega, such that beta is equal to 2 times delta omega. 2 times delta omega, such that if you use that, you will get one equation that beta is equal to, or first I will write it as delta omega value. It's a very big derivation, we got the result already. See your notebooks. Delta omega is equal to, yes, R by L. Delta omega equal to R by L. Remember, when we have started using this L, C and R, the 3 or 4 pairs that are very important as a conceptual question that is asked. We have seen in the last class, L by R, we call it as an inductive time constant. So L by R, this ratio has the dimensions of time. Similarly, we said C into R, inductive capacitive time constant. So dimensions of L by R is same as dimensions of CR, and the same was the case of the resonant frequency. 1 by root LC we have given frequency. Therefore, dimensions of root LC all have the dimensions of time. Other reciprocals you consider, you will get the dimensions of frequency. Remember the combination of LC, LR and CR. Now here we got delta omega is equal to R by L. Therefore now you can calculate what is that omega 1. Omega 1 is, yes, 1 by root LC minus R by L, and omega 2 value is 1 upon root LC plus R by L. I am telling you, straightforward questions will be there with numbers, with numericals, or small changes. What is the possibility of changes of omega naught or changes of this value of beta? So what you find that this delta omega is R by L independent of capacitor value you will find here. Earlier we have told that omega naught resonant frequency independent of R value. Now here what do you find? Therefore now beta is equal to 2 times R by L independent of capacity. Now earlier we have shown that if the value of capital R changes, naturally this curve is going to change. How it is going to change? See, one more conceptual thing and also an example. How? Earlier we have shown, supposing this is for some R is equal to 20 ohm. R is equal to 20 ohm. Supposing, and in this case, this is what is omega naught, and these are half power frequencies, omega 1 and omega 2. Okay. Now supposing if I said for R is equal to 10 ohms, what are the different possible changes that you will expect? Now you see when R value, see here, when R value is decreasing, delta omega decreases. And also depending upon the value of L also it is inversely related. So this delta omega relation with R and relation with L, no relation with C. Supposing in this case no changes in L and R values, any changes in C, the same curve that we get. Now let me show. Supposing if it is for 10 ohms resistor, then what you find is that same curve where the peak comes at the same frequency, because omega naught independent of R value. Therefore the peak position and omega naught does not change. Rather what we find is that, yes, this is what are the new half power frequencies. Half power frequencies will change such that, what do you observe? If it is omega 1 less than omega naught, it shifts towards higher side, whereas omega 2 shifts towards lower side. A beautiful observation will be a solution for the most tough and intelligent question. How these values changing? Every time when I have told you expression, look at the expression for LHS and RHS and try to analyze what are different possibilities of the changes that are in the examples. Right, now you see. One more definition after these half power frequencies and bandwidth. So what is the expression for bandwidth? Beta is equal to 2 times R by L. Now, we are defining an important parameter. For any device, when it is in the working condition, how efficiently the device is working is an important thing. So for an LCR series circuit, for its efficiency now, it is not exactly efficiency term, but you can take it as a measure of efficiency. How better it is functioning and what for. So depending upon that, now here we give a parameter called the quality factor, Q factor. The quality factor, otherwise we have called it as sharpness of resonance. Sharpness of resonance, an important condition. 2-3 expressions. Again we'll give. Now here Q, how did we define earlier? We define it as beta, which is a ratio of, yes, resonant frequency to bandwidth. Resonant frequency and bandwidth ratio. Remember, beta is not delta omega. Earlier we have mentioned that, no confusion, it is 2 times delta omega, because according to me, delta omega was omega naught minus omega 1 or omega 2 minus omega naught, whereas beta is omega 2 minus omega 1. We have taken this delta omega to calculate half power frequencies, so that is why my convention was 2 times delta omega is bandwidth. Now, this definition can also be redefined as, I will write it as VL by E. This is voltage across inductor. In resonance state, in the state of resonance, VL, and this E is the applied voltage. Both have been instantaneous. VL by E is also a Q factor definition, and also we can write it as VC by E also. Again VC for voltage across capacitor in the state of resonance. Now, also it can be defined in terms of energy also. So here it was earlier in terms of frequencies, here in terms of voltages, and here in terms of energy if we get. It is total energy stored in the system. Total energy stored in the system by energy lost during single period. During single period. That period refers to, of course, the F, the frequency, reciprocal term, the time period term. So during that interval, whatever energy is lost, that is what is defined as Q factor. Now all these things when we are writing, all are in the case of course, resonance. Even this is energy loss during single time period. That is, it is referring to that energy loss dissipation in the resistor in the form of Joule heating, like that. So total energy stored by, this one is also the definition, which will give you the results as, now Q is equal to, you have omega naught is 1 upon root LC, and that beta value you got it as, yes, 2 times R by L. R by L. Remember, no confusion with respect to 2. Maybe some of the books you refer, you may don't find this 2 because they have taken delta omega as omega 2 minus omega 1. For that such expression, you don't get this 2 term. No confusion, please. So this value, you will get it as 1 by 2r under root L by C. Now we have seen the cases omega naught independent of R value, right? Beta value independent of C value. Now this Q factor is the term, is a parameter that depends on all the three L value, C value and also R value. Remember, you have to practice few things as I have told you, expressions for resonant frequency and expression for bandwidth. Afterwards, it is simple substitution and getting your formulae in 5 or 10 minutes, then substitution of the data. Too much of memory, definitely, in the examination hall, it gives a lot of stress, and that is why try to reduce the memory and try to improve the logic. So this is the discussion that we have followed for the LCR series circuit. Practice it once or twice.